Let us start this lecture with a thought process from Winston Churchill. Success is not final, failure is not fatal. It is the courage to continue that counts. So, in the last lecture basically we had initiated discussion of how to analyze a single droplet under quiescent atmosphere, and of course under zero gravity condition, considering the flow to be one dimensional in V-sheet flow and other assumption we have already discussed. And what we will be doing now, we will be basically looking at all these conservation equation one by one and try to do some approximation, and let us see how we can solve it analytically. And overall mass conservation equation, if you look at, as we are taking, is a steady process. So, therefore, this will be 0, and then we will get this 1 over r square d by d r square rho v. This is basically, if you look at what is this term, can anybody tell me? This is nothing but your mass flux, right? How much mass is moving out per unit area, these are the mass which is going out, fuel mass, right? And that is saying basically mass flux into area is basically mass is conserved for all that, all radial location. If you look at, this is the all radial location, it is basically remaining constant mass, right? But however, mass flux will be changing, okay. And this is our equation 1. Keep in mind that V is the bulk velocity, rho is the gas density, right. And momentum conservation, of course, we have seen one dimensional situation. Actually, there is no need because pressure remain constant. We have seen premix flame and then kind of things. We have already seen that. So, there is no need to discuss anything. So, species conservation, if you look at, this is your basically the convection term rho r square v dy I by dr, y is the mass fraction of I s species, and rho d, d is the diffusivity, rho is the density, into d by dr in the bracket r square dy I by dr into m dot triple dash I r square. This is basically source term, and this is diffusion term, this is your convection term, right. So, if you look at this term is basically, I can write down as m dot double dash r square, because rho v is your mass flux and I can write down. And keep in mind that your Lewis number is equal to 1, right. Lewis number is equal to 1, right. If it is Lewis number equal to 1, I can of course substitute this thing rho d as, if Lewis number is equal to 1, that is basically means alpha by diffusivity kg by rho Cp into d. So, I can write down rho d is equal to kg by Cp. We will use that later on, okay. And as I told earlier that yi is basically is the mass fraction of ith species. Ith species means it can be fuel, it can be oxidizer, it can be product, right, kind of things, right. Ith species means F will be a fuel, like we will be writing oxygen is oxidizer and P is product. So, now let us look at energy equation. It is similar term, this is basically convection terms, and this is conduction term, and this is your source term, the heat release being done here. So, what we will do is basically we will have to solve these equations, right. If you look at, this is your source term, which is non-linear in nature, which is quite difficult to solve. So, you keep in mind T is the temperature, Q dash is the energy release rate due to chemical reaction. So, let us look at the single step chemistry. As usual, we do take F moles of fuel reacting with 1 mole of oxide going to 1 plus F moles of product, and from this we can actually like look at how we can connect these species and energy conservation equation, or in other words how we can solve them, looking at basically single step reactions, and we need to relate this thing to the heat release rate as follows. We can do, that is basically mass consumption of oxidizer per unit volume is equal to m dot triple dash F divided by F is equal to product P divided by 1 plus F and Q dot triple dash by F delta SC, right. So, this is we can do that thing, and from this if you look at, you can find out very easily, that is Q dot triple dash is equal to delta SC m dot triple dash F is equal to 0. So, if you look at this thing, now we can use to simplify our equations, basically to overcoming the source term. So, look at, let us see energy conservation equation, and we have already discussed this, and let us consider the fuel species conservation equation, right. And what we can do now, what we will be doing, we will be basically multiplying this equation 7 with delta SC, right. I can multiply it with the delta SC, right, and then add that equation to the 3. That means, we can add equation 3 with the 7. So, if I will do that, what is happening? This term is equal to 0, because already as per the equation 6 we have already seen, right. So, if you look at these things, these are all terms which has to be changed, because I can club this together, because this looks to be similar terms, and the diffusion on the right hand side of this equation, this is the diffusion terms from the energy equation, and this is from the species equation, which is similar in nature, right. Provided we will invoke the Lewis number equal to 1, right, and already we have seen that this kg by rho Cp, right. If you can look at this one, right, I can write down for Lewis number equal to 1 is nothing but here rho by d, right. I can write down this one, already we have done that, this is right, or I can use that as a rho alpha, because this itself is equal to basically rho alpha, right, because what is alpha? Alpha is equal to k by kg by rho Cp. So, that means rho alpha is equal to kg by Cp. So, I can use any one of them, and then so that both are same, right. And so, if you look at this, I can write down basically here itself, this is m dot r square, I can write down as d by dr Cp T plus Yf delta Sc, right. I can take that on the left hand side. In the right hand side, I can take this as a basically rho alpha, right. I can take this as a rho alpha, then rho alpha d by dr I can write down this r square into d by dr Cpt, right, plus Yf delta Sc, this term, that is all, is not it. So, this is the equation we can get, right, and by this basically we call we have eliminated the source term, and this expression is basically known as Schwab-Zeldovich transformation. We are basically doing that, and it will be only possible if the Lewis number equal to 1, otherwise it is not possible, right. So, I have already written this expression earlier, right, and as I told that we have eliminated nonlinear source term in this analysis, and this is known as Schwab-Zeldovich transformation. And what we will be doing basically, we will be non-dimensionalizing it and trying to express this equation 9 in terms of non-dimensional variables, right. What we will do, we will basically divide this equation by Qv plus delta Sc Yfs minus 1, right. I can divide this entire equation, right, and that will get into the term, because already we have seen this is the heat of vaporization, this is due to the combustion, right, all is coming, and we will see that why we have taken this term little later on, right, and then if we do that, then we can express this m dot r square dB Ft. Ft means what? We have considered fuel and temperature, right. Two equation we have considered. So, therefore, I am writing Ft. I can also consider fuel and oxidizer. I can also consider the oxidizer and temperature. Any two combination I can overcome the linear, and this is rho alpha r square dV Ft. What is this Bft? Bft is basically this term Cpt plus Yf delta Sc divided by Qv plus delta Sc Yfs minus 1 in the bracket, right, entire thing has to be divided. So, this Bft I have already shown here, and similar way if you derive, you can get other relations, right. Keep in mind that this Qv is equal to heat input required for the vaporization of droplet, Yfs is the mass fraction of species at the surface of droplet, right, and Cl is the specific heat of the liquid, and delta Hv is basically heat of vaporization, right. And other conjugate variable involving oxidizer will be like this, you can get, right, you can derive that as well, right, by considering the similar procedure you can get. And there is another one is Bfoxt, is basically Ya plus Yox f divided by Yfs minus 1 plus Yox at the surface, this S stands for surface into f, right. F is the basically the stoichiometric. So, let us consider that how this we can solve, because this is the equation we have derived, right. We will be now looking at how we can solve it. So, this is the equation which we will be solving, and I have not considered now Ft, right. It can be anything, it will be similar form, whether for Ft or for your Fox or Oxt, right, it will be similar. So, that is why I have used this B. And what we will have to do now, basically we will have to use the boundary condition, right. The boundary condition, if you look at what are the boundary condition here, at R is equal to Rs, from the energy point of view, what is happening, right, we will have to carry out a energy balance, because this is not very easy, okay. This you will have to use basically a energy balance, how much heat is coming in, how much is being, it is getting vaporized. So, we can say that this at that I can write down energy balance, right, will be m dot f into QV. This is a vaporization, the amount of heat which will be coming into for vaporization is this is the total amount of which will be reaching the surface, right. How it will be coming is basically is equal to kg dt by dr, because of gradient, you know, along the direction. So, heat conduction is coming, right. Due to heat conduction there will be the transfer from the flame to that, right. And I can write down this as kg by Cp, and I can write down Cp here, right. And keep in mind that this kg by Cp is nothing but your rho alpha and d Cp T by dr, right. And now we will have to look at, this is one, we have done the energy balance at the surface of the droplet. Now we will have to do also mass balance, right, because the vapor is going out, it is getting vaporized and getting out, right, it will be moving out the vapors, right. So, therefore, we will have to look at that also mass balance, right. So, mass balance we will have to look at surface at R is equal to Rs. So, what it would be? It will basically again this m dot f, right, will be nothing but your m dot f y f s minus rho d d y f by dx. This already we have done, this is the bulk due to the bulk, and this is your diffusion, right. And let us say this is I will say this is something, let us say A, because I will be using some different number A, and this is your B equation. Now, what we will do? We will have to basically multiply this equation by delta SC, right, delta SC, and then add this equation to with the A, keeping in mind that we are using the Lewis number equal to 1, and therefore, instead of this I can write down this is nothing but your alpha as Lewis number equal to 1, right. This is as Lewis number equal to 1, and so what we will do? We will be basically getting now, if I will do this, this will be by adding equation A and B, right, after multiplication of delta SC, okay, we can get m dot f, I can say this is basically Q V plus what it would be delta SC, right, yfs minus 1 is equal to rho alpha dCpt plus delta SC yf divided by dr. This will be dr. Okay. This is dr. What I will do? I will divide this equation. I can get basically is equal to rho alpha, I can take is d by dr bft, I can do, right. How it is? Because bft is nothing but your Cp plus Cpt SCYF divided by QB delta SC YFS minus 1, right. So, it is coming similar way, right. So, I can write down then my boundary condition, right, at I am combining these two at R is equal to Rs, okay. R is equal to Rs is nothing but m dot f rho alpha dV by dr, R is equal to Rs. This is the boundary condition I am getting, right. And now you have understood why we have divided earlier this QB delta SC YFS minus 1, right, because of this is the balance, then we are, because this is the amount of heat which will be taken care for this mass to move around. And when R is equal to infinity, what will be B will be B infinity, is far away from the flame, far away from the droplet, far away, it is not here, it is far away, okay. So, with this we can what we will do, we will integrate this equation 11, right, twice and apply the boundary condition, right. So, if you look at, if I will do first, let me do, that is basically the first ones. If I will integrate the equation 1, I will get m dot f r square b is equal to rho alpha r square dB by dr plus c, right. So, that means now I will have to find out the constant c by integrating equation once, first we are doing. So, what we will do at boundary condition, we know that is at, this is your boundary condition at R is equal to Rs, what you are getting? You are getting basically m dot f is nothing but your rho alpha dB by dr, R is equal to Rs, right, is not it? So, if I say this is Rs square, and I can say this is Rs square also, right. From this equation I can say this is basically C, and putting this boundary condition in equation C, I can get m dot triple dot f Rs square Bs is nothing but your m dot triple dash f Rs square into plus C. So, therefore, C becomes m dot triple dot f Rs square Bs minus 1, right. This is my C, right. So, then equation C becomes, right, let me write down, equation C becomes m dot f r square b is equal to rho alpha r square dB by dr, then plus m dot f r square bs minus 1. And we will simplify further, and we will discuss this and how to we can do. Let us say that this is equation D, and we will be discussing the next lecture. Okay, fine. Thank you very much.